We'll do a quick overview of LiDAR as it relates to transportation. It's important that everyone is familiar with certain concepts, though, and that's what we'll be covering. We'll take a high-level look at what components are involved with this kind of system in the context of transportation. Then we'll do an examination on what LiDAR sensors are and a little bit on how they work. After that, we'll cover the role that perception software has in the solution. Starting with the high-level architecture, a LiDAR solution generally involves two components in the context of transportation: the LiDARs and the perception software. First, you have the LiDAR. These are the sensors. You can compare this to the role your own eyes play in capturing visual information of your surroundings. Next, you have the perception software. The LiDARs will feed their visual information into the perception software where it makes sense of it all. You can compare this to your visual cortex, which is the part of the brain that makes sense of what your eyes are looking at, like identifying different objects around you. Putting it all together, your eyes, the LiDARs, capture visual information and send it to your brain, the perception software, which then makes sense of it all. This is essentially how LiDAR will work in the transportation context. Starting with LiDARs, they essentially work like this. LiDARs send out a beam of light, they wait for it to reflect back, they compute the distance the beam traveled, they assign a spatial point position for it, they add it to a list of measured spatial points, measure the next position, record, repeat. When all positions have been measured, sends all those points to a perception software and then starts all over again. This concept is generally the same for all LiDARs. However, almost no LiDAR is the same. The details of their operational characteristics influence what they're good at and which ones you should choose. The choice considerations list contains some of the operational characteristics you should concern yourself with. For example, spinning LiDAR have moving parts, but usually provide omnidirectional view around the LiDAR. Solid states generally provide a focused view, like a fixed camera would, and generally have longer ranges. The field of view impacts where you install it and how many LiDARs you may need to ensure complete coverage for the perception region. Scanning strategies and laser channels impact performance of the LiDAR, much like the FPS metric in cameras. The wavelength that the LiDAR uses may impact resolution, distance, and performance in certain weather conditions, although some of this can be compensated for by the perception component these days. The type of LiDAR, perception region size, and site characteristics will ultimately determine how many LiDARs you need in order to achieve optimal coverage. Now, if needed, you can mix different LiDARs, which lets you take advantage of the pros and cons of each depending on where you plan to install them and how you plan to use them. There are other things to consider, but for the sake of brevity, the key takeaway here is that the LiDAR you choose, may be the difference in a successful or failed deployment. So be very deliberate in the choice you make here. The next component is the perception software. The way this works is that it essentially consumes spatial points from the LiDARs, fuses them into a single 3D point cloud, processes the point cloud to identify objects, runs algorithms to classify the detected objects, and then provides output interfaces for other systems to integrate with and use to process data. One important consideration for this component is that each perception software may only support a certain set of LiDAR. So one question to ask yourself when choosing the perception component is, what LiDARs do they support? Also consider, it may be worth the perception provider's time to add support for a LiDAR they don't already support. So if you have a specific one in mind that they don't support, you can always ask if they're able to add support for it. Next, fusing together the point data from the separate LiDARs into a single 3D point cloud is a critical function of the perception software. How this gets done depends on the perception software, but the concept is generally the same for all of them. There are many advantages to this fusion, which will become apparent later in the presentation when I explain the benefits that LiDAR provides in transportation. The last step is to process the single 3D point cloud data to both identify objects and classify them. This component really outlines the differences between perception solutions. Some of them use machine learning and AI. Some have specialized algorithms to compensate for things like occlusion and ghosting. Some learn their environments, improve over time. Some have algorithms to filter out noise, like noise that adverse weather may introduce. Some can detect objects and classify them with only 3 points. Some can detect and classify static objects, which is significantly harder than classifying moving objects, and many more.